Sorry, welcome everyone to the October Saturday morning astrophysics. I'm glad to see so many people here today. Today we're going to do a really fun interactive activity. Have you ever wondered how astronomers are able to determine the age of some planets? We actually have the method for that here today, and we're going to be doing an activity where we can determine the age of Mars based on craters. This lesson is going to be led by our own TA, Mariana. Mariana is a graduate student here at Purdue. She part of the EAPS department, which means Earth, Atmospheric, and Planetary Sciences. And she's going to be running through what we're going to do today. So, Mariana, do you want to take it from here?
Thomas, before you turn it over to Mariana, I just have to make a comment. For all of you out there in middle school and high school, Mariana got her start with SMAP. She attended SMAP as a high school student here at Purdue. That was in the day when we did SMAP on campus before we started to do it remotely. And so Mariana came to us and spent a couple of years doing SMAP on campus. And now she's back on campus, having completed her undergrad degree, and now is working on a PhD in planetary science. So that's an inspiration for all of us to see what Mariana has done. So I'll turn it back to you, Mariana. Go ahead and take it over.
Okay, thank you both for the introduction. I'm really excited to give the lesson today. And like Dave said, it's especially exciting to be able to teach SMAP as a previous student many years ago. So let's go ahead and get started. So I'm going to share the PowerPoint. All right, can you all see that? Okay.
We can.
Perfect. Okay, so we're going to be determining the age of the surface of a planet today. Okay. So what can you learn from craters? Does anyone have any ideas? Go ahead and unmute yourself or put it in the chat.
Maybe like what materials struck the planet or how big it was.
That's a great point. Anybody else have any suggestions?
I would guess like a lot of the history behind like the object.
Yeah, that too, definitely. Yes, Naomi.
So we can get a rough idea of how many impacts it's undergone. Although some of the craters may be eroded, but I guess you can get a rough estimate.
Yep, that's also a really good point. Yeah, so you can learn a lot of things, like you guys said, what the impactor was made of, what kind of material it hit, the history of the planet, and maybe how many times it was impacted. So today, we can learn about how planetary scientists use the number of craters to guess how old a planet's surface is. And so planets begin without any craters on the surface. It's completely smooth. But over time, the older the surface it becomes, the more time passes for more craters to be able to hit and be kind of mark the surface of a planet. So these two images are just showing how a planet's surface can change over time. And so larger impactors are actually less common than smaller ones. And so that means if we see a planet that has a lot of really big impactors, that must mean that it must be older to allow more time for these big impactors to hit. So this is a video kind of simulating what it looks like when a planet's surface is being hit by craters. So I'll just play it through so you guys can see. And while you watch, take note and kind of make some observations about what you see. While we watch, if anyone wants to unmute or chat, what do you see? What kind of observations do you have?
A lot of the bigger craters manage to like stay there longer, at least have a lasting effect on the geography, where a lot of the smaller craters go away pretty quickly.
Yeah, definitely.
There's still that big first crater in the right that's been there since the first part of the picture there.
Yeah. I'll play it once more if anyone else has.
A lot of the craters seem to fade away after some amount of time.
Yep. Yep, exactly. And that's kind of related also to the size. If it's bigger, it takes longer for it to go away over time.
Seems like other craters hitting the same crater, like if crater 1 is disrupted by crater 2, crater 1 seems to go away slower.
Mm-hmm. Yeah, exactly. Yeah, that's a lot of really good points. Also another point, what is the most common size that you guys see for these craters?
The smaller
50.
ones.
Yes.
Like 20 to 50.
Yep, the smaller ones are definitely most common. So that's great. All right. We can count the number of craters on a planet's surface, and we can use this to determine how old or estimate how old the surface is. So how do you think this works? Does anyone have any ideas?
Just availability, and if you're setting aside luck, you have to have the existence, the time window so large or large enough that you can have this many craters. If you have a lot of large craters, it means you have to have existed for long enough to be able to gain those large craters. And either that or you're very lucky and you just got hit by like 3 large craters in 10,000 years.
Exactly. Great. So you're thinking like a planetary scientist. So older surfaces have more time to accumulate craters compared to younger ones. And so what might cause a planet surface to appear younger than it actually is? Does
When
you have ideas? Naomi?
And some of the oldest craters can be just eroded or volcanism or just erosion or maybe kind of washed out by other craters, for lack of a better term.
Exactly. I was going to ask how it can become eroded. So that's a great
like
question.
wind and water, wind, rain, dust, water, it's just the atmosphere alone corrodes.
Yeah, those are all really good points. So yeah, it can have formed later. It could have been eroded, like you guys said, volcanism, water, the atmosphere, all those things. Great. So each of you should have received an image of Mars' surface. So we're going to analyze that. But first, let's talk about how we can do it. So first, you don't have to do it yet. So I'm just going to give a brief overview of what it'll be like, and we'll go more into depth. So basically, you're going to circle everything that looks like a crater on your image when you go to the breakout rooms. And each image is going to have a scale at the bottom. So for example, in this picture, the scale is 250 kilometers. And so you're going to use a ruler and you're going to measure to see how many centimeters this is. And so you're also going to use that ruler to measure all the different craters that you've circled, and you can make a list of their sizes. And so how can you do this? Using a ruler and a scale bar to determine how many kilometers the craters are. So we'll be using this equation. So whatever the diameter of the crater is in centimeters using your ruler is going to be equal to whatever the actual distance is in real life in kilometers, which we don't know that number. And you're going to multiply that by however long your scale bar is, measured by your ruler and by what it says. So just a clearer example, the diameter of whatever your ruler is for the crater size is what you're going to be solving for green. And that takes into account the scale bar's distance, so 250 kilometers in this example, and that's multiplied by whatever the scale bar is in centimeters. Is anyone confused about that, or does that make sense?
Mariana, let me ask a question. So I'm looking at your green ruler there.
Yeah.
And you're measuring that one crater that looks like about maybe 1 centimeter. Am I reading that correctly?
Yeah, that could be one. Yeah.
Okay. So you've got a crater that's 1 centimeter, and then you're going to then what's next?
So I'll get into that. But yes, so
Okay.
you're going to use that ruler, and like Dave said, you're going to measure, okay, you see that crater? It's 1 centimeter. So you'll keep that in mind for when we do the next part. But yes, that's a great question. Cool. Does anyone else have any questions or any confusion about the equation? You should have received a document that has like a big table on it. That should also, I believe, have the equation as well. but I'll give you guys a second anyway to write it down. So let's do an example. So we measured a scale bar with our ruler to be about 10 centimeters. And the picture shows that the scale bar actually represents 35 kilometers. And we measure a crater, we know the distance because we sent a rover or something, and we know that it's 4.5 kilometers. So what should the diameter of this crater be in centimeters? So we have this equation and we can plug in the values. So we're solving for the crater diameter ruler measurement in centimeters. We know that the crater distance is 4.5 kilometers, so we can plug that in, multiplied by what we measured the scale bar to be, which was 10 centimeters, and we divide that by what it represents, 35 kilometers. Some units can cancel out, and so when we solve this equation, we find that a crater that is 4.5 kilometers is the same thing on our paper as 1.3 centimeters. Okay, does that make sense? Great. Cool. So we're going to be doing this exact procedure on your Mars paper. So you're going to count each crater that fits in a specific size group. So for example, you're going to be counting every crater that's 256 kilometers, and you're going to put that into a group, count the number of those. And you'll do this again for all the sizes of craters that you see on your picture. And so you're going to fill in a data table. And so this is a similar example to what you should have on that document that was sent to you. And so you're going to be able to convert all these kilometer values. These are the groups you're going to be measuring for, and you can count the number that fit into these groups. So these numbers, they're in an exponential pattern. So when you count a crater, you're going to be putting it in the size group that it closely matches. So for example, you measure a crater that you think is 200 kilometers, but there's no group here that's 200. So you're just going to put it to whichever it's closest to. So you can put it in the 256 kilometer group. So just basically round it to whatever you think is closest. Okay, now we're going to talk about Mars and introduce the surface we're going to be looking at. Mars has two main hemispheres. It has the northern lowlands. The differences here, the darker region are the lowlands, and the brighter regions here are the highlands. What differences do you notice between the two?
Mariana, I'm going to interrupt you for just a minute. There was Malaika in chat mentioned things about Mars. Mars is said to have a chance for life due to the presence of water. So it's probably a good point. I think we're discovering more and more. You're the planetary scientist, but aren't we discovering more and more that Mars does have a sizable amount of water?
Yeah, so sorry, I didn't see the chat, but yes, so definitely there could have been life at one point. We don't think that it's there anymore if it was ever there. But it's basically confirmed. There's no real discussion. There was a lot of flowing water on Mars. We see evidence of dried up lakes and rocks that have basically interacted with water, become eroded. All these kinds of signs that show that, yes, there was water there. And so maybe, like Nathan said, that Mars was habitable a couple billion years ago. So yeah, and also Isabel said that there was an atmosphere at one point, and yes, there was, but over time it basically escaped the planet, and so that's why it's kind of cold and desolate there now. So yeah, so those are some really good points. Thanks for pointing that out. I did not see the chat. But yeah, so there's also the hemisphere. So does anyone notice differences between the two hemispheres?
The southern hemisphere seems to have a much higher elevation in the geography and topography, but it also has a much larger crater.
Yeah, so it has a lot more craters. That's a great point. Why do you think the two are so different, or how could they have become so different over time?
The orbital erosion?
Maybe. Any other ideas?
Maybe volcanic activity.
Volcanic activity, yeah, that's a really good point. Yes. Yeah, so those are yeah, Naomi, go ahead.
There's also I believe the planet's wide ocean some time ago. I believe it was mostly in the northern hemisphere.
Yes, that's what I was going for. So there's a theory that maybe the whole upper part of Mars was covered in a global ocean. And that's maybe why we don't see as many craters up there, because they were all eroded over time. And so that's a really great point. But the other options, we really just don't know. So they could also be true, definitely, for sure, volcanism. There are a lot of volcanoes in that region as well. So it's definitely something that's up for research these days. So those are great points. So let's do an example of crater counting with the lowlands, or the upper hemisphere. So we have this picture here with the red grid lines, and it says, anyone guess how many craters are in this picture?
40.
40. That's a great guess. Anyone else?
Maybe
60.
50?
Sorry, what? I heard maybe a 60. Okay, yeah, so 40, 60, yeah, those are some great guesses. If you look really, really closely, I counted 91. So I circled them all here, and you can see kind of what I was going for here. So there's 91 craters in this picture, probably more, but they're just too small to see. And I also measured the scale bar with my ruler, and I said that it was 1.7 centimeters long, but it represents 100 kilometers. So now let's convert and do an example calculation of 256 kilometers to centimeters. So we use our equation that we had before. We plug in the diameter distance of 256 kilometers. Our scale bar ruler measurement was 1.7 centimeters divided by a scale bar distance of 100 kilometers. We calculate that, and we see that any crater that's 256 kilometers or close to that will be around 4.4 centimeters with our ruler. Okay, so now we can fill in the second column in our table. So we put 4.4 centimeters is equal to 256 kilometers. Can anyone do, let's have some people do 128 kilometers, and they can do that example calculation. And then we'll have some other people, if they can try and do 64 kilometers. And then once you have it figured out, I'll give a minute or two, and then we can give the answers.
So Mariana, we're not saying that there are any craters that are 4.4 centimeters. We're just figuring out how we can look at the photo and count the craters for each category.
Mm-hmm. Yeah, just because it's on this table doesn't mean they're actually in the picture. It's just so you have an idea of what kind of things you should look for. And so when you measure a crater, let's say 8, and this is not the answer, but let's say 8 is half a centimeter. You know that anything you measure that's half a centimeter will fit into that group. So just a quick way to be able to identify. So the ruler measurement was 1.7 centimeters, Naomi. Sorry, yes. Okay, so we have someone that says 128 kilometers is 2.2 centimeters. And yes, that one is correct. Does anyone know about 64?
I think it's 1.1. Yeah. Or like 1.08. Yeah.
Yeah, we can round that to 1.1. So that's great. Did anyone get anything different or is confused about how we got that? Okay, so those are the correct answers. So we can fill out the rest of that column. I will let you guys finish it on your own time in the breakout rooms, but it seems like you guys are on the right track. And so I measured each crater in the previous picture of the 91 craters that I counted, and I put them in the groups that I thought they were in. So I counted 21 craters that were around 8 kilometers and 70 that were around 1 kilometer. So now we need to calculate how many craters there are per kilometer squared. So how can you do this? Basically, you'll measure the length and width of your picture using your ruler. So you'll get a certain amount of centimeters for that. And you can use the same ratio equation that you just used to convert that to kilometers. So you can use those values once you have them in kilometers and use the simple area equation, length times width, to find out what the area of the whole image that you circled was. So for example, you found 13 craters that were around 4.5 kilometers. And you calculated the area to be 200 kilometers. So what is the number of craters per kilometer squared that were 4.5? So you do number of craters, sorry, divided by the area. So it'll be 13 craters divided by 200 kilometers squared, and you get this number here. And you do this for each group that you found, so 256, and so on. And then you can graph it. So in this graph here, on the x-axis, we have the diameter of the craters. And then on the y-axis, you have the number of craters per kilometer squared. So you should have a graph of this for Mars, which that's what you're going to use in the breakout rooms. But basically, your x value is whatever the size of the crater was. So for this example, it would have been 4.5 kilometers. And your y value is this number we just calculated, the 0.065. And so the TAs will help you in the breakout rooms, but this is how you're going to place a point here. And so you'll do it for each group. So each colored point is a different size group of craters. So 256, 64, 8, that kind of stuff. And then you'll make a line that will best fit all the points. And then whichever line, you see the dash lines. So whichever line you made that's closest to a dash line tells you how old the surface is. So for example, here we have a line that's between 1 and 4 because the GY means billion years. So this planet, for this example, must be between 1 and 4 billion years old. So let's do this for the lowlands. So we calculate the area. So
Mariana, could
yes.
I go back to that previous slide?
Yes, one moment. Here we go.
So in this example, the craters that have a diameter of 4.5 kilometers,
Mhm.
and looking at the circles that you put on the graph, I don't see one at 4.5 for the diameter.
Yeah, this is just an example one. I didn't
Okay.
actually put like a
Okay, I
kilometer.
just didn't want to miss something. Okay, got it.
So so you guys don't get confused. The 4.5, this is not an actual graph of that, just an example of what it should look like. But yeah, that's a good point. Any other questions? Okay, if there is, hopefully I can clear it up. So we'll calculate the area of the lowlands that had the 91 craters. So I found a length of 9 centimeters, which I calculated it and converted it for you. So it's about 530 kilometers. And the width was 7.8 centimeters, or about 460 kilometers. We calculate the area, so we multiply these two numbers, and we find that the image that I analyzed that is in the red box is about 240,000 kilometers squared. So now we can take those numbers. So 21 divided by 240,000 kilometers squared. We calculate the area. We can calculate that number. So 9 times 10 to the negative 5. And we can graph that point now. So here is the graph that you guys should have gotten. So this is on the x-axis crater diameters. So this region over here is kilometers, and this is number of craters per kilometer squared. So our x value, we said it was 8 kilometers. This group of 21 craters is 8 kilometers. So we go here, we find 8, and then our y value, we calculated it to be around 9 to the negative 5. So the TAs can help you on this part, but it should go all the way up here and be graphed here in this region. And then we can do this again for the 70 craters that are 1 kilometer, and we get this number, which is graphed right here for 1. So you can see it here. And then we can make a line that best fits them. So it doesn't exactly have to fit each point, but as long as it's a straight line that fits one of the dashed ones. So between these two lines, they had a line here that fit, if you can kind of see that dash here. So I put a line there that best fits between the two, and that points all the way down to 3 billion years. So that means these Martian lowlands must have formed about 3 billion years ago. Just as a quick summary, you're going to circle everything you think is a crater. You're going to make a list of what they are after you measure them with your ruler. You'll use this equation to transfer everything, which we already did 3 of them for you on the table. Then you'll count the number of craters in each group, which you can put like a tally mark on your table just to count them easily. And then you'll calculate the number of craters in a specific size group, divide it by the area, and graph your data, which the TAs will help with. So that's the general procedure, and it should be on that paper with your table as well, so you can look over that again. But yeah, so now you're going to be analyzing the Martian highlands, so the lower hemisphere. So you guys will do this crater graphing, split up into teams, split it up however you'd like in your breakout rooms, and you'll get to estimate how old this is. And so as a point as well, graph, so do the crater counting within the red bars. So going back, you can see in your image, there's little black lines over here to the sides. So only do the crater counting within those. So this is your area that you'll calculate later. So keep that in mind. But yeah, so this is what you're going to be analyzing in your breakout rooms. So now we're good to go.
Mariana,
Yes.
I have
Sorry.
a question.
Yes.
What about craters that are like split on the grid
Yeah.
lines?
So I would say anything that's split on there, count it as well. So these big ones here to the top that look like they're cut in half, you can count those too. You can still see what the diameter would be, so you can count those. But yeah,
Thank you. But yeah, does anyone have any questions before we get started that they weren't able to ask when we were all in a big group?
Well, I know they asked this before we went into breakout rooms, but there's some craters that are like they're split, right? But they're like more outside the grid than inside, you know?
Yeah.
So how would we count those?
You know, if there's a decent portion of the crater that's within the grid line, then I think that would, you know, count it as long as you're able to measure the diameter. But if it's just like the tiniest little sliver on the edge of it, you know, maybe don't count it.
Once you measure a couple of craters and you see how they are relative to the others, you probably don't have to actually physically measure every one. You could eyeball it. You see a crater that is, maybe 0.25 centimeters, and just look around and see, okay, you've got 20 more that appear about the same size. I don't think it's necessary to really measure every single one.
I finished and I got around 211 craters.
Okay.
Okay. Anyone else?
I got 207 craters.
Okay. That's good. We're getting estimates that are within reasonable margin of error of each other. So that's pretty good. Who wants to take the upper left quadrant of the image?
I can take that one.
Okay. How many of who wants to take the upper right quadrant?
I can take the upper right quadrant.
Okay.
Okay.
Lower. Now, who wants to take the lower left?
I can.
Okay. And then to the remaining two people, if you haven't picked one, you'll take the lower right. So what you want to do next is basically determine which of these craters are 200 or of each kilometer group, and then basically multiply it by that ratio of the scale bar ruler measurement to the scale bar distance.
One point, for example, I'm looking at the upper right or upper left quadrant. I see 1, 2, 3, 4 craters that are about the same size. And
Yes.
so, I think it's okay to eyeball them. And if you measure one, you can just approximate that the others are in the same category.
Oh, yeah, absolutely.
That'll speed things up a little bit.
You also see a lot of small craters in that quadrant that are around the same size. So you could eyeball those too.
Yeah, I'm looking at the lower right quadrant as well, and I
Yeah.
see like 1, 2,
There's
3,
a bunch of
4,
them. Yeah.
6, 7 about the same size.
For this picture, we just have this one big crater that is the most dominant one, and then we have the 1, 2, 3, 4 here. They're about the same. We're counting this one, I'm pretty sure, on the edge here. Has anyone measured this quadrant? Does anyone have a centimeter measurement for this one?
2.5 centimeters.
Okay, Caleb. So you measure, so presumably this is the biggest crater that we have here. So which crater group would this crater be in?
128 kilometers.
128 kilometers. Very good. So we know for a fact that in the 128 kilometer crater group, we have just one crater. And we know that in all these images, the total area, like mentioned in the slides before, is about 240,000 square kilometers. So how would you calculate the number of craters per square kilometer? Anyone?
You would divide the number of craters in that crater group by the total area.
Right. That's it. So your answer would simply be 1 over 240,000.
All right. So we cut you a little short on time, but I hope everybody has the right idea. And you can finish this on your own and be your own planetary scientist. Mariana, go ahead and wrap up and let's see what you got.
All right. So does anyone have, because you guys were talking about it, any estimate on how many craters there were in the picture? It depends on the person. There's no right answer to this, but Naomi?
According to my count, okay, around 160, 162.
Okay, yeah. So
I think our group got around 120 in general. I know someone counted like over 200.
yeah, so those people, you guys are all going above and beyond because I did not count that many. So you guys are doing a great job. So this is what I found. I think I counted like 50. So you guys did a really good job. There's some small ones I left out, you can definitely see. But this is about what I got. So I didn't go into as much depth, but that's okay. And so this is what I graphed. I graphed 3 main groups, and I kind of fit a line that was in between all the points, and that gave me a straight line. And so this gives me a result of about 3.5 to 4 billion years old. So this area was formed billions of years ago. So this is what, if you decide you want to finish this on your own time, this is about what you should get. And you might get a little bit of a different answer. That's totally okay. But it's billions of years old, which is a really cool way to just have a simple picture and determine how old something is. Why would you think there would be different results between people? Why, if you finished in time, like what would you think would cause some differences? Isabel.
Well, I think David was talking about it in our room. He was saying that like each person can determine like it's like own rules kind of for this type of like measuring. So someone might take like a split down crater, or some might take like only the big ones. For example, I was counting also like really small ones. So that's why I got such a high result.
Exactly. So yeah, so I didn't count the super small ones, so that's why I got such a low number, but some people in one of the breakout rooms got 200. So definitely it just depends on whatever your personal opinion is on what a crater is, or what looks like a crater in the picture. What did you notice about the craters in the picture? What did they look like?
A lot of them looked more like ovular than circular.
Yeah, there are a lot of oval ones. Isabel?
Well, I noticed like some of the bigger ones have like a peak in the middle.
Yeah, exactly. So that's actually called a complex crater. And so when you have a really big impactor that comes in super fast, basically, you know, when you drop like a pebble in water and it bounces and then it comes back up and then shoots back down. Basically, that's what happens, but with rocks. And so that little pebble at the top is basically it bounced up and then solidified before it came back down and flattened out. So yeah, so that's a really good point. Yeah, and only the big craters have those. The small ones don't. So that's how you know. Yeah, so that's a good point. Did anyone else have any other observations?
There are a lot of overlapping ones.
Yeah, exactly. Lots of overlapping ones. I also noticed there were some craters that looked more eroded than others. So there's if you could look at this picture for hours and find new things. So yeah, those are all some really good points. So why do you think a planet might be younger in one location, but older in another?
And there may have been lava flows or something to sort of cover up any some of the craters that were already there. So I guess it's stay surface rock and craters are younger, even though that part of the planet isn't necessarily.
Yeah, great point. That is definitely true. Isabel?
Well, I think we were talking earlier about like water placement. So yeah, maybe around like the top there was like more water or more activity happening, so like it might look like more washed out.
Definitely, for sure. If there was an ocean, it would have eroded a lot. So maybe that's a theory why the lowlands didn't have as many really big ones, because the images were the same size, same scale. So, but they were really different. So, yeah, good points. So this is an example. So this is Olympus Mons on Mars. Does anyone know what it is? Like what kind of feature is it? Naomi.
It's a dormant volcano, and the tallest one in the solar system.
This is the biggest volcano in the solar system. What do you predict the age of this region might be? Like how old would this one be? Because really you can't see any craters, except maybe a few at the top. But what would you predict the area age might be? Nathan.
If I had to guess, it might be around 2 million years old because the volcano had to form. But at the same time, it could be a lot earlier, or the area could be a lot older. Because if the volcano did erupt around that time, it could have just reformed the landscape and any craters along with it. So.
Exactly, that's correct. So the area dates, if you were to measure the ages of the area, around 2 billion years. So that means that any craters, there were definitely craters there that formed like 3 billion years ago, but they got covered up by the lava with the last eruption. So whenever the last eruption happened was the last time any craters were able to be erased, basically. So yeah, so that's why you might have some differences in different regions as well. I'm a PhD student in, like Thomas said, in the Earth, Atmospheric, and Planetary Science department, but I study the planetary side. And so I'm studying how life can begin on a planet. So specifically on how it started with Earth, and then how it started like billions of years ago, 4.5 billion years ago, and then how it can begin on like a moon such as Titan, which is around Saturn. Which is a very different world compared to ours. So I'm studying how life can start on these planets. And so I was a SMAP student back in 2018, a long time ago. But basically, doing activities with SMAP, I was inspired to learn more about astrophysics and also planetary science, which inspired my love to continue science when I graduated high school. And so I've been doing this for the past 6 years, and my love has never decreased at all. So I just want to know this is a great way to continue and inspire yourself to do more work, and hopefully one day you can study space as well, or other interests as well. So so yeah, it's been really great teaching you all. If you have any questions, please let us know, but that is all that I have prepared today. So thank you all for participating.
Yes. Thank you, Mariana. That was a very, very fun activity, I think. And it looks like we got some really good results going on.
Oh, I was also going to like note that I really appreciate like the last part of the session where like you tell a little bit of about how you got here, right? Because I'm interested in following like a career in astrophysics. So it's interesting to know like the different paths you can take to go into different topics.
Mariana, I think that was directed to you. You did a good job on
Thanks. I'm definitely glad that that was helpful, and hopefully you continue to follow your own passions as well. But if you guys have any questions or want to talk more about how to get into science as a career, definitely we're available. You can email Dave and we can chat some more. So yeah, but I'm glad you guys enjoyed that.
Isabel, you are in Geo's class, is that right?
Yeah.
Okay, all the way down in Medellin, South America, Medellin, Colombia. So
Yep.
thank you for being here. Give Geo our regards, will you? Tell him hi.
Yeah, I will. I will.
Okay, Thomas, let's wrap up. What do you got?
I guess just thank you everyone for coming here today. I hope everyone enjoyed this session. From what we were talking about, it looks like everyone did. I sure enjoyed popping into all the breakout rooms and seeing what everyone was doing and the results everyone was getting. So with that, I think we're good, unless there's anything I'm missing, Dave.
I think we're good to go. Thank you everyone for joining us, and I really appreciate your feedback here at the end.
Thanks.
Bye-bye.
Bye.
Bye. Bye. Thank you.
Bye bye.
Bye. Thank you. Have a good day.